chaos. How quantum materials hold the key to a new generation of superconductors. Suchitra Sebastian, University of Cambridge, United Kingdom.
When the wall came down, I was in India. I was very young, and I remember thinking, but East and West Germany seem so different. What will happen when they come together?
Good morning. Thank you very much for inviting me. It's a real privilege to be here. So today I'd like to talk about quantum materials. And these are special materials with very exotic properties determined by quantum physics, which the previous speaker spoke about. In particular, I'd like to talk about a special type of quantum material known as a superconductor. So these materials carry electricity perfectly without any loss, and these have the potential to transform our energy landscape. So technology has been progressing very rapidly over the last few years. We're used to computer processors that are so small that they're smaller than a grain of rice. And these contain millions of transistors. Very soon, we'll all be driving electric cars that can be controlled by smartphones. But this rate of technology progress is not something to be taken for granted, and it's something that is limited unless we look for new types of materials. For instance, transistors can't be made much smaller, and so this is something which will require new materials to be looked at. The electric grid is something that supports all of these new gadgets. For example, smartphones consume a lot of electricity. And if we were to download data, say, at the rate of a video a week on a smartphone, this would consume energy equivalent to a refrigerator. So the rate of consumption of electricity is quite a lot by these devices, and they're connected to the electric grid, which is powered by fossil fuels. So these, as you're aware, are not an inexhaustible source of energy. So we're looking at renewable energy sources, and this is something that is an important realm that we need to explore. So all of these devices that we're looking at are immensely powerful. Actually, I read the other day that the current most popular children's toys are powered by computer processors equal or more powerful than the first mission to the moon. So we're used to a very rapid rate of development of technology, but looking ahead, how can we sustain this? So looking at renewable energy, superconductors are extremely important for this. So let me tell you a bit about what superconductors are. So when you think of conventional metals, you think of electrons that carry electricity, and these travel as single objects, right? So you have isolated electrons that bump into each other, that bump into the crystal lattice, and when electric current flows, it's not a perfect flow. You have inefficiencies, and when electric current flows, only a percentage of it comes out at the other end. In contrast, superconductors are quantum materials which conduct electricity perfectly. And how do they do this? So if you take a superconducting material, cool it down below a certain temperature, a quantum transition happens. At this quantum transition, electrons lock together into pairs by quantum entanglement, as the previous speaker spoke about. So you now have pairs of electrons. But what's more, these materials are now quantum materials which contain millions of pairs of electrons. So we're not just talking about one or two, we're talking about millions of pairs of electrons all collectively interacting. So that's just shown here schematically. You have pairs of electrons, but all of them are interacting together. So what this means that when the material is cooled below quantum transition, all these collective pairs of electrons condense into something known as a quantum condensate, or you can think of it as a quantum soup. So essentially what happens is that electrons at every point in the condensate are correlated with every other electron. So all of these behave together as a single quantum object, which is incredible because it's practically realizable. And what I'll do now is to show you a demonstration of some of the properties of superconductors. So what you see here is a vat of liquid nitrogen. And as you see, this is quite important because superconductors currently have to be cooled down below liquid nitrogen temperatures for them to show these properties of superconductivity. So one of the important properties of superconductivity, in addition to carrying electricity perfectly, is that when current flows perfectly on the surface of a superconductor, it expels magnetic fields. So what I'll show you is actually sort of a small-scale version of something that superconductors have been considered potentially useful for, is magnetically levitating trains. So what I'll show you is that a superconductor can levitate on what you see here. This is a magnetic rail, and it consists of magnets here. Klaus, can you come up and help me? So Klaus is just going to show you the magnets that make up this rail. So the superconductor that I just put into the liquid nitrogen should be cool by now. So I'm going to take these out. And I'm going to position this above this rail made up of magnets. And you can see that it levitates. And if I give it a little push, it'll go around the rail. And if there was no air friction, it would go around perfectly as long as the superconductor was kept cool. Another property of these superconductors is that they're pinned into position above the magnetic rail. And I can show you this by turning the rail around. And I'll put the superconductor underneath. And you can see that it's also quantum pinned below the magnetic rail. So I'm going to put the superconductor beneath the rail now. You can see it also levitates beneath the rail. And when I push it, it will move around the rail by this quantum pinning effect, which means that it doesn't fall and it's continuously suspended below the rail. So this is a demonstration. Ah, there it is. I lost track of it. So this is a demonstration of superconductors and how... So what you've actually seen is quantum physics in action, right? So the currents that flow on these superconductors are because of electrons that pair up and carry electricity perfectly. So this might seem quite exotic, and you might think that this is something quite unfamiliar. But actually, superconductors are probably something that you've come across. So if you've heard of the Large Hadron Collider, so this has a very big ring to accelerate particles, and it's actually 27 kilometers circumference. This is a giant superconducting magnet. So what this comprises, as I mentioned, is billions of pairs of electrons. So in effect, this is a quantum condensate of electrons that persists over 27 kilometers, which is incredible. You're seeing quantum entanglement of electrons over several kilometers. So quantum effects have very practical applications. If you've had an MRI, or if you're familiar with an MRI, the superconducting magnet is what drives an MRI. So if you have your head inside an MRI chamber, that's a superconducting magnet. Looking forward at practical applications, so I spoke about renewable energy, and actually this is something that is immensely important application for superconductors. So this is a picture of the night sky, and so the lit up areas on here are areas where electricity is most consumed. These are urban areas. The points on here, the green points and the yellow points, are where solar and wind energy are concentrated. And as you can see, these are quite far away from the urban areas. They're located offshore, they're located in deserts. And it's very important for us to transport energy if renewable energy is to become a source in the future, we have to think of how to transport it over thousands of kilometers. Current technology, which is AC conventional metallic electric transmission cables, first of all, they're inefficient, and secondly, they're not stable enough to carry electricity over such large distances. So this is not a technology that is possible to be used if we're thinking of such long transmission cables of thousands of kilometers. But DC cables of superconductors are an ideal alternative since they're perfectly efficient. And actually, this is not complete pie in the sky. We already have prototypes, and Essen is one of the shining examples of urban cities in which we already have superconducting cables. So a cable of 1 kilometer long has already been installed in Essen. This is a picture that you see between two substations. So electricity in Essen is already being carried using superconducting cables. So how do we move from a cable that's 1 kilometer long to something that's thousands of kilometers long? One of the challenges, as I mentioned earlier, current superconductors need to be cooled down to liquid nitrogen temperatures for them to work. And if we look at the progression of superconductor discovery, over the last 100 years, we've progressed quite a bit. We've come from materials that only superconducted close to absolute zero. Now we have materials that do work at minus 100 degrees, so at liquid nitrogen, which is not too inaccessible. But this does pose technical challenges of cooling them down, of making them last over long distances. So how do we make better materials? How do we progress from there? It's been 20 years since we've discovered the last superconductors. So one of the reasons this is a challenge is that these materials are driven by quantum physics, and understanding how millions of electrons interact is a challenge. We don't yet know how to relate this quantum physics of these materials with the materials' properties. Which materials will be the next superconductors? This is a challenge. So what I and my group are doing is to try and transform this process from a serendipitous process. So at the moment, all these materials were discovered accidentally. But what we'd like to do is to move to a process which is directed, a process of discovery where we predict where superconductivity will be found, and then we look for it and anticipate it, and thus make better and better superconductors. So what we've been doing is, first of all, using very high magnetic fields to look inside a superconductor to tell us what the electrons are doing. And what we know now, using these tools, is that the best superconductors were almost not superconductors. They're on the verge of being magnets. They're on the verge of being insulators, which are the opposite of superconductors. So this gave us a clue, and what we then realized was, how about we take materials that are magnets, that are insulators, and put large forces on them to turn them into superconductors? So we started with a material known as an iron arsenide. That's a very good magnet. The region in blue is a magnet. It's a very good magnet at ambient conditions, and we're all familiar with magnets. These are everywhere. These are not particularly extraordinary. They're quite ubiquitous. So we start with a magnet that's quite a bad metal. It doesn't conduct electricity very well. But we take this material and put it under large pressures. And these pressures are similar to those of the Earth's core, where new materials are created. So we put large forces on this material. The principle of applying pressure is like the tip of a stiletto heel applying pressure. So we put these materials between the cullets of a diamond anvil, press on it, and we discover that dramatically, with a very small change in volume, these materials transform into superconductors. So this is like quantum alchemy. We've started with a non-superconductor, transformed it into a superconductor. And this is an ideal way to populate the landscape of superconductivity. We currently have very few examples of superconductors near liquid nitrogen temperatures. But if we're able to directly control materials, create more of these superconductors by design, we're on the route to creating optimal superconductors close to room temperatures. And looking at applications, applications will range from electric transmission cables to magnetically levitating trains to superconducting chips to gearless wind transmission. Thank you, class. So quantum materials are going to underpin technology in the future. And we're looking at the brink of a quantum materials revolution. Thank you.